Okay. Um, so we're going to just uh, go through the rest of the LDA part. I just mentioned latent terrestrial allocation, which is the multi-topic model. At the end of last class, I'm just going to go back to that and then talk about some issues there, and also talk about what is involved in doing inference with that model. Okay, and then actually for the specifics of deriving the Gibbs sampling, you really need to look at the papers that I provided. I think there's in particular the specific paper which has the derivation of the Gibbs sampler. And I think I also sent a message to the Piazza sort of giving an overview of the steps involved. The reason I'm not going to go through this here is because unless you have background, a little bit more background in doing the Dirichlet integrals, it's not worth going through the actual mechanics here. The advantage for us is that finally the Gibbs sampling simplifies to just keeping track of counts, the number of times a particular topic is occurring, a particular word is occurring in a topic, and the number of times a topic is occurring in the document. And these counts are being used to essentially do the posterior computation. When we say posterior computation, that is we'll wind up computing PZ given W, where W is the words, which are the only things you observe. And so you're trying to compute the conditional distribution of the topics given words. And once you have that, you can then get the theta and phi back. By the way, in the slides that I'm using today, there are slides taken from different sources, and unfortunately, each of them use slightly different notation for the model. Okay, so in particular, when I first show you the model, I'll show you which parts will keep changing in terms of the notation used. Some people put actually, I think the JMLR paper used beta for the topics. Okay, but then it uses alpha for the hyperparameter. Okay, some other people basically try to use alpha and beta for hyperparameters because there are two hyperparameters, one for the Dirichlet of the topics and one for the Dirichlet of the words. Okay, and then wind up using phi and theta for the two continuous variables, the two multinomial distributions. Okay, so you kind of have to. Unfortunately, I just noticed that there are these variations, but so you might get confused a bit on that. But let me try to get you through the ones that I have. Okay. So anyway, going back to what we were discussing last time, so we basically had this the progression of ideas here is unigram model assumes that all documents are drawn from the same word distribution, and then the single topic model assumes that word distributions are topic dependent, which is good, except that it also assumes that each document has only one topic. Okay. Now, by the way, this is also called the mixture model. We call it. So you can think of these ideas, topics. You think in terms of topic models when you're thinking about words, but you can also essentially think of what is happening here is each topic is a distribution over words. Okay. A mixture model basically is one where the entities that you are seeing, in this case documents, could have been generated from one of k different mixtures, k different distributions. And it's called a mixture model because you mixed up all those distributions. Okay, and so when you look at the documents, you don't quite know which distribution the document is coming from. Okay, and so when you're doing inference or learning, in essence, you only observe the words. You only observe the words in the document, and you have to also figure out which topics they came from, and from that figure out what the distribution is. And the word mixture model actually is also close to this whole idea of basically so mixture of Gaussians is something that mixture of Gaussians is a model that gets used a lot. So suppose you're only actually just seeing, let's say, one particular point. Okay, let's say I have let's say 2 Gaussians. Okay, and then obviously this Gaussian is likely to give points. I mean, these are unidimensional Gaussians. So this Gaussian is likely to give x values here with higher probability, and then values of x going far away will become lower probability. And then this one will have these x values, the higher probability. Okay, so now if I see a bunch of points, okay, now the question of course is, suppose I see this point, is this point being generated by this Gaussian or this Gaussian? It could have been generated by both. Do you see what I'm saying? Okay. Clearly, it has a much higher chance of being generated by this than this, because by the time this Gaussian reaches this point, I mean, again, I'm putting x values on the x-axis directly. Okay. So another way of thinking about it is that suppose I have 2 Gaussians on the real number. Okay. So basically, these are all real numbers, and this one is centered, let's say, at 100, and this is centered at, let's say, 500. Okay, so if I have a point 700, is 700 being generated by the Gaussian centered at 500 or the one centered at 100? Okay, so that is what you will have to figure out when you're given a bunch of points, and then if I just tell you that these are the points and they all come from a single distribution, single Gaussian, you can fit a single Gaussian. Right? You can fit a single Gaussian. Basically, you would just take the mean and the variance of these points and then say the Gaussian with that mean and variance is the best Gaussian if you have a single Gaussian. But if I tell you that that's not really what I generated this with, I generated with 3 different Gaussians or 2 different Gaussians, okay, then you need to figure out where are the means and variances of these 2 different Gaussians. See what I'm saying? What you're doing there is not that different from what you're doing here. The only difference is here the distribution is multinomial distribution, and here the distribution is a Gaussian distribution. Okay, so so here essentially, so the same thing. So if I give you a bunch of words from documents, and I just say, well, just figure out the word distribution. And if I don't tell you there are any topics, then it's so much simpler to just figure out one single multinomial distribution, because you, for each word wi, let's say word horse, you see the number of times the word horse occurs in all the documents divided by the total number of words occurring in all the documents. That would be the horse probability, and then you can smooth it a bit. Okay, that's very simple. Now, but on the other hand, if I tell you that really, even though I'm giving you these 15 documents or these 100 documents, they are actually drawn, I mean, these documents are drawn from 3 topics. That means 3 Gaussians or 3 distributions. Okay, now tell me what is the word distribution for each of these topics. Clearly, there is a lot of freedom here. You need to figure out where you're going to put these, the 3 multinomials. You see what I'm saying? Okay. I mean, actually, the word that I used, where you are going to put, that makes more sense from the point of view of mean of a Gaussian distribution. But really, all I'm saying is each topic has a different multinomial. Okay. You need to figure out now 3 different multinomials, not one. And to do that, you need to also, as part of this inference, figure out which word, which document is generated from which topic. And this is where the EM occurs. This is where the expectation maximization comes in. In fact, mixture of Gaussians is in the way you actually solve the mixture of Gaussians is by expectation maximization. So if you look at the textbook, okay, if you look at the textbook, the example they give for EM, one of the examples they give for EM right after the Bayes network example is the one where you essentially figure out the mean and variance of the mixture of Gaussians. If I tell you up front there are 3 Gaussians that generated this data, can you figure out what are the means and variances of those? And they actually do that by EM, expectation maximization. Okay, so that's what you will wind up doing to invert the model here. So one way is generation, the other way is inversion. So if I tell you the story, then you need to figure out the parameters for the story. And part of what I'm saying is that this story is very easy to figure out the parameters because there's just only one distribution. This one, it becomes harder because there are k distributions and you need to first sort of do this iterative thing, the way EM works, which is, let me assume that document 1 is topic 1, document 2 is topic 2, document 3 is topic 3, and it repeats. 4 is 1, 2, 3, etc. Okay, and let me assume this way, and then use that to figure out what are the, so you use that, so that's the parameter estimation. Based on that, you do the inference, and then you do the parameter estimation. This is basically what the EM winds up doing. Okay, but we are not going to stop there. Now we're going to go to the next part, which is more complicated. Here you are actually going to say that a document is a specific mixture over topics. Okay, so there are k topics. Previously, each document was directly one topic, one of those k topics. Now each of the documents is some mixture over these k topics. Okay, so there are like 2 kinds of mixtures going on. Topics themselves are mixtures over words. Documents are mixtures over topics, so they are mixtures over words. Okay, now the interesting thing, of course, is that the number of different types of documents you could get here was basically, number of different types of documents you could get here was just 1, because there's only one type of document. There's only one distribution, statistically speaking. Here you had k types of distributions. Here, even though it's any point on the k dimensional simplex, because there are k topics, and providing a distribution over the k topics would give you a topic mixture, and there are infinite number of topic mixtures. Okay, so upfront, if I sort of made you feel worried about how am I going to get the topics here, just given the documents, because there's a hidden variable, the topics. Now I have 2 hidden variables. Now I have the topic hidden variable and the mixture hidden variable. Okay, so LDA is going to be more difficult to invert than even the single topic model. Okay, actually, I think so this one, so this is called, in statistics, this is called the mixture model, and this is called the mixed membership model. Again, the names are useful because even though we are doing it with respect to like words and language models, essentially they are also relevant for other types of data. They don't have to be linguistic data. Okay, these ideas, some of these ideas are very much relevant in other places too. Okay, okay. So basically, then you're looking for a document-specific mixture over topics, and so what that actually means, interestingly, is that now documents can actually be seen as, you can say that the documents used to be vectors in a v-dimensional space before. V is the number of words in the vocabulary. Now all of a sudden they have become vectors in a k-dimensional space where k is the number of topics. Okay, and that reduces the dimensionality of the documents. Now, you might say that, well, previously here, they were actually one-dimensional. I mean, so they're still k-dimensional. So again, I keep saying this, last two classes, I think I said this. In this case, the documents were in the k-dimensional simplex, except they were only at the corners. Because it had to be, one topic has all the probability mass, everything else becomes zero. Okay, here you are saying they are any arbitrary point in this k-dimensional simplex. And so there is also this reduction, dimensionality reduction that goes on, along with this. Okay, so we've looked at this, right? Basically, the generative model is I'm generating these words, essentially having picked the topics, k topics, and for each topic I pick the distribution over words, and then for a document I have to pick a topic mixture, saying which topic with for how much probability, and then I essentially sample from this mixture and decide, okay, the next word is going to be topic 4. So then I go to 4th topic's distribution, so that word will be now picked from this distribution. So the words with high probability in this distribution are more likely to be picked than the ones with lower probability. Okay, now one thing before I go forward again, I think I mentioned this last time, which is if I just give you a bunch of documents, all of these guys have the same exact input, unigram model, single topic model, LDA model. They all have the exact same input, which is the documents with the words in them. Okay, right? So one can argue that, look, the rest of whatever they are doing is the assumptions on the process that generated these documents. These are just assumptions. So the question is one set of assumptions better than the other set of assumptions? Who is to judge? Well, who is to judge is basically, as I said last time, you could see which one is more predictive about the documents that have not yet been seen. So suppose I have, let's say, 1 million documents, let's say 10,000 documents in some particular collection, let's say the ACM collection, ACM Computer Science Papers collection. I have 10,000 documents. So I'm trying to figure out the top, basically, I'm trying to model these documents. Okay, so I can take 9,000 of these and say I'm going to train myself on these. 1,000 of these I'll put in a vault, randomly. Okay, now I'm going to give these 9,000 documents to this guy, and this guy. Each of them will essentially come up with a way of modeling the data. So this guy will pick one distribution, this guy will pick k distributions, this guy will pick k distributions and also topic mixtures. Okay, and then the question then is, they have to, with respect to each of these models, you want to see how surprising are the 1,000 documents that I have kept away. Remember, these documents, these 1,000 documents and these 9,000 documents, they all used to be happily living together. I just picked 1,000 out. So if you really learned the model here, it's like learning the lingo, right? If you learned the model here, then you should be not surprised with the documents that I kept away. And for that, there are measures basically the measures of perplexity, which are sort of like the likelihood of the data given my model. So for each of these guys, I can then compute the likelihood of these other 1,000 documents given this model, this model, this model, and see which one has the highest likelihood. And I would say that is the best. You see what I'm saying? And to the extent we are actually spending all this time talking about LDA and not stopping here or even not stopping there, is because actually in most cases the likelihood of the data will increase if you assume there were topics and if you assume that there were mixtures of topics. And the entire evaluation in the JMLR paper, where they are comparing themselves to others, who are they comparing to? They're comparing to single topic model and unigram model. And they're saying we are better. Now, better in what sense? Better in that we are less surprised by the held out data than the other guys are. And it's a kind of a unintuitive model. It's not that they are completely generating these 1,000 documents that I have in my hand, right? They cannot rewrite that particular document. It is just that they are going to be less surprised by those documents, given the model they have. And the surprise is in terms of likelihood. Okay. Okay. So anyway, so this is how this is the story of the generation of the documents, and as I mentioned, okay, so and this is basically the picture of that story. This is the probabilistic, the Bayes network picture of this story. Okay, so what we are saying here essentially, so you start looking at the plate picture. So there are n documents in each word, n words in each document. Okay, and so this is a word WDN. This is the nth word in the dth document, and it is generated by its own topic, ZDN. Okay, ZDN would be one of k topics, so it will be either 1 or 2 or 3, etc., up to k. Okay, and now say basically Z says I'm going to generate using 4th topic. Somebody needs to tell you what is the distribution with respect to 4th topic. So if you notice in the picture here, Z is these. Okay, so this one, let's say, is the second topic. So Z is the second topic. Now if I'm going to generate these yellow words using the second topic, I do need the distribution corresponding to the second topic separately. So that is sitting here. This is the second topic. So whichever is the yellow is the second. Okay, so in the model, basically you have the word WDN. It has as its parents the topic number as well as the topic matrix beta. Now, how does the topic matrix beta look? It basically is a V by K matrix. Okay, such that, so this is the first column is the first topic, second column is the second topic, third column is the third topic, and so on. Okay, and then essentially you put positive numbers between 0 and 1 here such that they add up to 1. Okay, so that's what we have in mind. So this beta, this looks, reasonably inconspicuous, is actually holding all these distributions, all the word distribution for the k topics. Okay, so now of course, if I were to tell you that get me the second topic and a word from a second topic, so I then go into beta and look at the the distribution in the second column, and then toss a coin, v-dimensional coin, and then whichever face it comes, that's the word that I'm going to put as that word. Okay, so then the next question, of course, is who is making these betas and who is making these Z's. Okay, so we are basically going out and saying that the Z's, the topics, are essentially being sampled from a topic mixture. Topics are being sampled from a topic mixture. So this is basically this platform. Okay, which is a multinomial distribution. Okay, and so I am going to essentially, so that this theta is a multinomial distribution. Okay, and this is basically, it's a vector of size. It's a vector of size. What? Number of topics, size k. So let's assume always k is the number of topics. So theta is a vector of size k. Okay, the interesting thing is the same topic mixture is going to generate every word in the given document. When the document changes, the topic mixture changes. Do you see what I'm saying? So that's basically shown by putting this theta d variable outside the plate corresponding to the ZD and WD variables. That means theta is the same as long as the document is the same. Right? Okay? And then of course, then basically, so for each document there exists just one theta, one topic mixture. Now, where is this topic mixture itself coming from? It is being generated from a Dirichlet prior. This is where finally we come to the priors. It's a Dirichlet prior. It's a k-dimensional Dirichlet prior. Now, it turns out that in Dirichlet priors, of k-dimensional Dirichlet priors, you can basically get, the hyperparameters can be alpha 1 to alpha k. Okay, and they can be any arbitrary numbers. One particular kind of k-dimensional Dirichlet prior is a symmetric Dirichlet prior, where all alphas are the same. So alpha 1 to alpha 1, alpha 2, alpha 3, alpha k, all the way up to, all the k alphas are just the same value. And so in that case, we'll just write that single value alpha. But the assumption is that you are actually doing that. You still basically have k hyperparameters, and they're all equal value. Okay, so it's sort of, we are, when, in most of these most of the LDA implementations, people just assume symmetric Dirichlet priors. Okay, so they actually just have to, to get this model going, they only have to give the prior, the hyperparameter for the prior distribution. That's it. Okay, and that would be given by the alpha value. Okay, and on this side, so that's basically, once I do this, okay, and as I'm saying this, you can actually look at this guy. This is an unrolled version of this. We'll talk about in a minute, but you can see that that is basically what we are supposedly writing in a shorthand form. Okay, and then on this side, the interesting thing is the topics are not at all document dependent. The topics have no connection to documents. So documents are only corpus dependent. So the topic cannot live here, it cannot live here. So it makes its own separate. It makes its own separate, plate. Okay, so the topics are beta 1 to beta k, and each of the topics are represented essentially by a multinomial distribution. Just like here you had theta, here you have beta 1 to beta k, and each of these, of course, are multinomial distributions over the entire vocabulary. Right? So again, picture here. So these are multinomials on the number of topics. So if you have 15 topics, then you need a multinomial distribution over 15 topics. These are multinomial distribution over the number of words in the vocabulary. These are much more painful looking things. These are basically, million dimensional if you have million words in the vocabulary. Okay, now of course, if you're thinking, this is basically what you're doing. So one of the questions, of course, is do people actually have million dimensional distributions? How many of you are far enough ahead in your projects, the LDA project? And did you know what actually your program did? You figured out your topics. What? Yes. I understand. So how big were these distributions? I'm talking about, I don't need to use the notation. I'm talking about, this is the distribution over the vocabulary words, and this is the distribution over topics. So the question is, how big was so you needed this distribution to be as big as the vocabulary. One thing that people tend to do is they artificially reduce the vocabulary size. using basic simple IR techniques. Things like the word the would just be ignored. Those are called stop words. You ignore them. Okay, you can also ignore any word that only occurs in the corpus, it occurs less than 3 times, let's say. You see what I'm saying? Okay. When you do that, then the effective vocabulary size may sometimes be much smaller. Okay, first of all, you only need to look at the words that are in the corpus because you're modeling the corpus. Okay, and the other thing, of course, is that not all words occurring in the document may actually be used. That's just a way to make your life simpler, so that you would have a smaller distributions that you're picking. Okay, but this is supposed to be a distribution over the vocabulary. Okay. Okay. So then, what else? So you have the betas are basically each of the multinomials on the vocabulary for each topic. Okay, and they are being picked. Each of these multinomials are being picked using the same multinomial prior, multinomial Dirichlet prior. And this Dirichlet prior has hyperparameter eta. Okay. So what I was saying, okay, this Dirichlet parameter has a hyperparameter eta. That means it basically has eta 1, eta 2, all the way up to eta v. V is the vocabulary size. I'm just saying all of those are same, equal to eta. Okay. And each of these topics are being picked up front by just sampling this Dirichlet. Do you understand what I'm saying? So now, and the last thing I need to tell you is, why is this dark? This is dark because in this entire model, the only thing you actually observed are the words in the document, nothing else. Okay, and so you need to compute the distribution of everything else given the words, the conditional posterior distributions. Okay, now I also want you to understand that the moment I gave you this picture, you are ready to start generating documents. You're ready to start generating documents. Why? I mean, one issue that you have to overcome, and at least, when you start looking at this model, is who is sitting down and writing these large distributions and these small distributions. Somebody has to write down, right? Do you understand what I'm saying? Where is that written here? It's automatic. Because you made your life simple by just converting everything into you just said there's a prior that generates the multinomial required. And there's another prior that generates the k topic multinomials required. The only thing I need to give then is the hyperparameters alpha and eta. Once I give that, I can sample the prior and get theta. And similarly, I can sample the prior k times and get k betas. Yeah.
So is it safe to say that we can initialize alpha and beta uniform distribution if we have a large number of documents?
So no, that is actually no, because the point is that there are some design. So the one part of the JMLR paper that's still sort of a black art is that they will talk about fitting alpha and eta using maximum likelihood estimation, while they talk about probability z given w being computed using the inference. It's putting first of all two things together. Okay, so one idea is if you're really doing Bayesian learning, then the problem with the Bayesian learning is there should never be any end to the regress. Okay, you have to put a prior on everything. So with this alpha, so there should be a prior on the Dirichlet hyperparameter alpha. And whatever distribution you give, there should be a prior on that. Okay, and then eventually the last guys are just hand given. Okay, so the assumption right now is we assume that alpha and eta are given, and then you know an MLE method would have actually tried to fit parameters, whereas a Bayesian learning method essentially just doesn't fit any parameters. Inside it just tries to compute PZ given W, which is the conditional positive. Now coming back to your question, since we are supposed to put alpha and eta yourself, what are the design decisions? It turns out that's where the properties of Dirichlet distribution come into. It turns out that if alpha is small, okay, a k-dimensional Dirichlet distribution, so first of all, let me show you these pictures. Okay, it's first of all hard to see Dirichlet distribution. Beta distribution, I showed you nice pictures, right? And you do remember that when we saw the beta distribution could look either like this, or even like this. Okay, now you can think of beta distribution essentially as a distribution over just two topics. It's a mixture over two topics. Right? Okay. Now this, you know, is now we are looking at mixture over three topics. That's it. Okay. So for the topic mixtures, there are some interesting issues we have to deal with, which is if everybody has every topic with a uniform probability, if you start that way, then this is what I was telling you earlier. I mean, there is basically no difference between topics and words anymore. Okay, you should assume that they basically you have to hope that the topic mixture distributions are sparse distributions. Okay, so it's like we are now asking more of your Dirichlet distribution. The Dirichlet distribution was supposed to previously just give a k-dimensional vector, you know, for the topic mixture, such that they add up to 1. That's all it was supposed to do. Okay, but now we are saying, no, please, when you give this k-dimensional vector, could you make it such that many of the entries are 0 and very few entries are non-zero? That would make it a sparse mixture. That means each document, so, and this is normally true. Now, if you take like something like ACM computing, you know, corpus, let's say, there may be possibly 100 topics, you know, the cyber security is a topic, you know, automated planning is a topic, something else is a topic. It's very unlikely that any single paper will have all 100 topics. Okay, people are into interdisciplinary research. Everybody says they are into interdisciplinary research. But try to write a paper which brings together like 100 different fields. You know, one word from each of the fields, and it would basically get killed, like roadkill. Okay, mostly what we expect is each paper, while it may not be from any single topic, it is at best from a small number of these 100 topics. So this one brings operations research and automated planning together, and this other one brings some statistics and cybersecurity together. The total number of topics themselves are 100, but individual documents are only non-zero probability for some of the topics. This is what you want to initialize your model. Do you understand what I'm saying? So now that's where you need to understand what's the right way to initialize the Dirichlet model. So these are all symmetric Dirichlets for 3 dimensions. Okay, this is a 2-2-2 model, this is a 5-5-5 model, this is a 2-2, well actually this is a asymmetric model. Okay, so this is a 2-2-2 and this is a 5-5-5. These are the kind of Dirichlets we are talking about. Now, the interesting thing is if alpha is less than 1, so the Dirichlets where alpha is less than 1, okay, would essentially generate sparse distributions. Okay, and so notice that if they're, these are all, let's say, so basically if alpha equal to 0.1, this picture would look how? So remember the picture here is shown, this is a simplex. The three-dimensional is basically, this is a three-topic simplex, and the wider it is, the higher the probability that that particular topic mixture would get. Again, let me go over this again. So here is topic 1, topic 2, topic 3. Okay, this point here is, let's say, 0.333, 0.333, 0.333. That's the probabilities. That point is looking white, that means it's been given high probability. Whereas this point here is 0, 0, 1. Because for topic 1, 0, topic 2, 0, topic 3, 1. According to this distribution, this point is given very low probability. That's why it's looking dark. You want exactly the opposite. You essentially want a Dirichlet distribution which is not white in the middle, but white in the edges. So it's sort of like this one. The n-dimensional analog of it. Okay, there's a beautiful stretch in that in the LDA lecture that Bly gave, that I don't know how many of you have watched, where he actually shows some, he actually samples the Dirichlets from low alpha and shows that they tend to actually give out more sparse distributions. When you're sampling, you're getting distributions and they are sparse. So that is a short answer. That's a very long answer to your question, which is, what should I put as alpha in the beginning? You should try to put alpha to be a small value. The values for the eta are not, there is no straightforward intuition on those. Okay. Actually, one of the other things that people do is you could try to pick between models. Like suppose you could try to put alpha equal to 0.2 and then alpha equal to 0.7, alpha equal to 0.9. Which is the right one? Well, you can then try out all, you can essentially model the data using all three models and see which one gives the highest likelihood to the held out data, and say that is the model, that's a parameter. That's the value. So in fact, they tend to use the language of fitting alpha and beta sometimes. The word of this whole idea of fitting is antithetical to Bayesian learning, because you never fit any parameters. But even in Bayesian learning, there are some parameters left over outside, because otherwise you have to infinitely just keep going and putting bias on those too.
So okay. The most generative model would be just to put a prior on alpha and
what?
The most generative.
No, there's no end to it. I guess whatever prior you put, that might have parameters, and I might ask, what is the prior on those parameters? You have to stop somewhere. Okay? Because there is no universal distribution that I know of from which everything comes, right? So whatever you put, suppose you were to put a prior on alpha, right? Then I will ask you, wait, what is the parameters for that prior? If you said uniform, that means it has a parameter. And I would ask you, are you sure really that it's uniform? Then you will try to put a parameter on that. And then we go back. Yes?
The model there, should theta be a plate because it's a mixture of topics?
No, theta is a mixture of topics. Yes. So what is the point?
So as in, doesn't that imply it's just one topic or something?
No. So okay. So let's now this one. Suppose I have this, and suppose I have three documents. And each of the documents have 4 words. Okay, and I have decided that, so each of the documents have 4 words, basically. Okay, then in that case, this is how the picture looks. The unrolled version of the picture looks. Okay, so the unrolled version basically is saying that, so the alpha is, you know, I can sample alpha once, I get a theta, another time, another theta, another time, another theta. And once I get a theta, then I basically generate the topics for individual words from the topics from the individual words and the topic distribution, I generate the word. So of course, in this particular case, the other thing was the number of topics is what? I did not tell you in this particular case how many topics are there. I started by saying, suppose there are 3 documents, because there are 3 documents. Each document has 4 words. This is the picture. I didn't say how many topics. Okay, that basically is the dimensionality of theta. And if I pick a dimensionality of the theta, then I should pick the same dimensionality, same number of betas. Right? If I pick 4 topics there, then I need to have 4 beta vectors. If I pick 10 topics there, I need to have 10 beta vectors. Okay? So did that answer your question?
Yeah, kind of. No, my question was in the model, because we are having, as in the beta, their topics, it's in a plate because it can be many topics.
Yeah, so basically,
so even theta,
so the right way to have written this, notice already, I was talking to you about yeah, so the beta here is being, so the another way of doing this is to actually write this as beta 1, beta 2, beta k, and eta is affecting all of them. Okay? Yeah,
so my question is, similarly, shouldn't theta be in a plate inside the document? Just a single node of theta for the document, doesn't that imply it's a single topic?
no, theta is, I'm telling you, theta is a k-dimensional multinomial. It's not a Boolean variable. So, okay, I hope you guys realize this. The real bad guys here is theta and beta. Because those are continuous valued variables. Those are continuous valued variables. Okay. That's right. Theta is this will be a discrete valued variable because it will take a value which is equal to the current topic for the word. This would certainly be a discrete valued variable because it will be one of the V different words in the vocabulary. These two are discrete variables. This, on the other hand, and this are continuous variables. Just wrote theta, but it's like a big vector. And the infinite number of those vectors. So it's a continuous distribution. Okay? Okay, so then basically this is what the picture, this is the unrolled version of the picture, this is the plate version, and this is the way you write, the generative process. So for each document, choose a topic mixture from the Dirichlet topic Dirichlet, whose parameter is alpha. And then for each of the n words, W1 to Wn, first you choose a topic for the word from the theta that you chose here. So the multinomial over theta. Okay, and then you choose a word from this particular distribution, Wn, given the topic and the beta, which is basically the topic distribution. Because this Cn becomes an indicator variable into this big data matrix. Okay, So this is really nothing but the distribution that I had on this side the previous example. Okay, and that's how these words are generated. And let me show you another picture. So suppose I had two. So this is just an example from the generative side. Okay. So suppose I had two categories. Category 1 had these are the words, and category 1 gives these probabilities for these words. Category 2 gives these probabilities to these words. Okay. Now, previously, if I had a single topic model, then I have to pick one of these topics. A category means topic, okay, and then I just basically generate the document word by word using just that distribution. Now, before I generate the document, I need to pick a topic mixture. The topic mixture is basically over just two categories, so it is in fact a beta. It's not even a Dirichlet, right? Because it's two topic distribution. Two topic Dirichlet is a beta, right? Okay, but that's okay. So here are, so I basically, a topic mixture is what's the probability that z equal to 1 and what's the probability that z equal to 2. And those two probabilities have to add up to 1 because we are assuming that the documents can only have these two topics. And every word in the document is from topic 1 or topic 2. So here is a 0-1 document. That means it's all second topic, no first topic. And if I just use these as the distributions and I sample words, I actually sampled it, you might get something like that. I sample it again, I'll get a different string. But again, remember my example of he and I both passing the same fair coin. He gets HHTT, I get HTTT. Okay, that superficial difference is not considered statistically significant. Okay, so this one is looks like this. If I have a 0.25, 0.75, it looks like this. 0.5, 0.5, it looks like this. 0.75, 0.25, it looks like this. 1, 0. Okay. So that's basically how that, and of these, really the ones that you would have been able to generate with single topic are this and this. The in-between ones are being generated by mixtures. Okay. So that's basically the generative part of the story for the LDA. Okay, and I'm going to say a few things about the inference part now. But are there any questions before I go forward there? One thing, if I could do, actually, I know I have, I'll show that in a second. Okay. I don't know if I sent it to you. There are lots and lots of people, lots and lots of examples of LDA analysis. Okay. So what we're going to do now is, I told you how to generate. Typically what you're given is the generated documents. You need to figure out what the topics are. And once you figure out the topics, then you could then use that to do all sorts of interesting things. Okay. One aspect, of course, is if I do figure out the topics, of course, is notice that now the documents have been reduced from as being vectors in a v-dimensional space into being vectors in a k-dimensional space, where k is just the number of topics. So it's a huge dimensional reduction. And if you're trying to compute the similarity between two documents which are both v-dimensional vectors, now you could instead compute the similarity between their two k-dimensional reduced versions. And those of you, how many of you have heard of latent semantic indexing? Okay, so basically LDA is a much more interesting version of latent semantic indexing. And when you reduce the dimensions, the inherent similarities might show up better. The noise gets reduced. You see what I'm saying? I mean, so a lot of us think that, you know, all the people from India look alike, all the people from like Ukraine look alike. Now, if you look at their shirt color and their hair length, etc., that doesn't make any sense. But we are clearly reducing dimensionality to some other level and then looking at the similarities. Okay, anyway, so the dimensional reduction aspect is also very useful here. But let me just show you a picture of what somebody did for NIPS. NIPS is this conference where actually the very first version of LDA, the 2001 version, actually appeared there. Anyway, so somebody last year took the 2012 NIPS papers, okay, and then basically tried to pick the topics. And then basically, one of the interesting things about learning the topics is if you were to learn the topics, if you were to infer the topics, then they would allow you a way of automatically organizing the data. Right? So when you go to NIPS, some people actually already organize. In fact, they don't do a very good job, especially in NIPS. They do an extremely bad job of organizing. I'm about to go end of this week, and this is 2013. Let's see, NIPS 2012. Okay, actually, I can show you 2013. So NIPS is this crazy conference that I'm going to have to go end of this week. And where am I here? It's 2013. What they wind up doing is they put all their papers as posters. Okay. Here, this is the schedule. And every night there are 90 posters. And you can see how nicely they are organized. You see the structure? You know which one you want to attend? Right. And if you, I'm somewhere out there because my student didn't want to go. Yeah, there. So that's just, you can't even see. Yeah, so there they are. So I'm somewhere there because this guy decided that he's going to, having his first child is more important than actually going to the conference. I mean, it's like the world has different priorities. Anyway, so this is how basically they put all the posters and you just go and look. Okay. In some other conferences, what happens? People tend to cluster. Okay, by the way, clustering is dimensional reduction. Okay, conference organization is a big deal these days. Mostly people who actually are running the conference will come up with some keywords and try to make, a particular topically connected 3-4 papers together. But those of you who have gone to conferences know that sometimes you can be in the wrong, cluster because there was no good cluster which is of the right size. Because not only do they want to cluster you, but they also need to cluster you into exactly, groups of 4 because 4 papers will fit in a session. So they would have things like databases and A-star search, which have no connection other than the fact that we ran out of sessions and there are 4 top papers left and we'll just put you together. Okay, but anyway, people try to do this and NIPS doesn't even seem to do it. So this guy, where did he go? If I have him still, I should have him here, right? Oh, this one. So what did he do? He essentially tried to say, let me think that there are some 7 high-level topics. And let me just, fit an LDA with 7 topics. And let the model tell me what the topics. This is basically what you're doing for your project, except this is on, NIPS papers. So we may have some idea as to what these topics are. So basically he just fit 6 topics, 7 topics, topics 0 to 6. Now what are these topics? They have no names. If you want to know what a topic is, you pick that topic and it will tell you the words there. I'm sorry, no. If you pick the topic 0, okay, actually the only thing we actually know are, so the way this guy did this is there is no single place where the topic distribution is given. It is just that okay, so if I pick topic 0, these are all the papers in topic 0. I mean, they have some connection to topic 0. That means their topic mixture provides a reasonable amount of probability to topic 0. Now, what is topic 0? These are the words that topic 0 gives high probability to. Okay, and then this is a topic 1 words, these are the topic 2 words, and you see that these are topic 0 papers mostly because their primary topic in the topic mixture seems to be topic 0. Right, if I have a paper which is 0.9 0.9 Bayesian learning and 0.1 neuroscience, then it's really a Bayesian learning paper. Okay, so it will get put in the first, it will be ranked as one of the first few papers in topic 0. So that's kind of nice, right? I mean, basically they just use the LDA model. They don't know what the topics are supposed to come out. Okay, and then it does get you to the extent now you can go look into it and sort of make sense of this. This is what people play, these games. Everybody looks at this and post facto tries to give names to these topics. But your program doesn't give that. Program is just giving you the latent dimensions, and then those will be useful for example, in 2 ways. One, of course, I can use the topics to browse the papers. So because NIPS guys did not give me a clustered, structured poster session. So apparently I also am told that this is the first time I'm going to go to NIPS, and I'm told that they have these poster sessions every evening from 7 to 12, and basically there will be alcohol flowing, and I guess the only people who are not drunk might be the people stuck with the posters. The people going between must be very well drunk. Anyway, so I guess how much of a structure you put in, it probably becomes moot at some point of time because the listeners are drunk. But they actually swear by it, and this is what they really like. And now this sort of a thing could give you interesting structure behind a flat organization. Okay, another thing is that I can actually take a particular, let's say, so this is, by the way, notice that this is one single paper, by the way. This is one single paper. And this paper had the following topic 0 words, the following topic 2 words, topic 1 words, and so on, with high probability. Now, I can also now actually give this particular paper, which is a paper in maybe a 40,000 dimensional space, assuming there are 40,000 words, that occur commonly in NIPS papers. Now it's become a 7-dimensional vector. And the coefficients of the 7 dimensions are the mixture probabilities provided to each of these topics.
Each of these words or
topics. But that's not shown here because we are using this tool right now as a browsing tool rather than as some sort of an actual, hidden dimensional, for providing the hidden dimensions of the documents. Okay, so that's something that I'll send you a link to this. You can also say NIPS 2012 LDA papers, and you'll get this. Somebody just ran this. You could have run this, and because actually it's possible because NIPS puts all the papers up, and so you can just crawl them out and then do it. Okay. And somebody else, if you search on the net, you also have Sarah Palin's emails. They found topics in there. Okay, and the one that started this all, that is actually much more interesting, probably, if I can get this. Is, let's see if I can get this. Oh, I have to go a lot. Just yeah, there, that's right. So this, by the way, is a picture from a paper by Griffith and Stivers, who essentially in 2004, they wrote this paper in 2004. I can send you a link to that too. These are the guys who first used collapsed Gibbs sampling for LDA inference. Okay, 2003 paper, the JMLR paper that you read, basically uses variational inference, which we didn't even talk about how to do variation inference. But so it turns out that that was a costlier way of doing inference, and so they found this more, sampling-based collapsed Gibbs sampling. Now the paper itself provides the first description of the collapsed Gibbs sampling that we talked about. But what they really were interested in doing is to use the LDA to sort of see how scientific topics evolve over time. Okay, and in fact, until this, I think this one has some 2,000 citations, because this is when people really paid attention to LDA, because they thought, oh, this thing actually can do useful kinds of analysis. And so what they did is, just like I was saying, I was doing my parochial example of ACM papers, and these guys were trying to submit their paper to Proceedings of National Academy of Sciences. So what do? You would analyze Proceedings of National Academy of Sciences papers, right? You don't say, we are doing ACM, could you please take our paper? So they submitted it to PNAS, Proceedings of National Academy of Sciences, which is basically all sorts of sciences, except most of these all sorts of sciences people, if you have ever seen them, they're all biology. I mean, I went ahead and ran and got my science, subscription, and every 3 or 4 years there will be a computer science paper. The rest of the time it's some random biology stuff. But anyway, so they looked at all these papers in National Academy of Sciences, and then they fit some topics to this. Okay, now first of all, before they fit their topics, they had to decide. This is actually a useful thing. Before they fit their topics, they had to decide how many topics to fit. So since they were writing a paper, they had a lot of time. So they considered fitting 200 topics, 400 topics, 600 topics, 1,000 topics. Okay, that means for each of them there is a different LDA model where there is a bigger beta matrix. Now, of course, here one topic is the unigram model, right? Now, the interesting thing is that, as I said, the way to figure out which is the right set of topics to fit is to see which one will give lowest perplexity for the held out data. So that's exactly what they did. Okay, so they kept some of these papers out, and then they computed the perplexity on those papers given each of these models. Okay, actually I think they just wrote the likelihood, log likelihood. They didn't write the perplexity. Perplexity should be lower, the better. Log likelihood, the higher the better. Okay, and you notice that the likelihood becomes high in the middle, which is what we sort of figured out in the very beginning, right? Too few topics, it's not going to be good. Too many topics, it's not going to be good. Because what's the best number of topics, by the way? No, as many topics as the number of articles. The Proceedings of National Academy of Sciences is so important that each paper starts a topic. Nobody ever cites anybody else. That way, it obviously will have the highest likelihood for the observed data, and zero likelihood for anything else, presumably, because you don't expect anybody else to be connected to anything you're doing, right? So anyway, so they actually did find that about 400 topics is where they're getting the best results. So then they basically went with this number of topics. 400 topics is a large number of topics, right? So then the question, of course, is how do you even look at the topic? So this is the topic number 37, this is 289, this is 75, etc. Okay, so now basically assuming that there were about 400 topics, that means every PNAS paper now is a 400 dimensional distribution. Okay, and you can then consider the topics that are hot. The hot topics are the ones that are appearing in every paper with a non-zero probability. Do you see what I'm saying? So for example, big data in computer science. Okay, whether or not you have any idea what it is, you throw in a couple of big data buzzwords and it will become a big data topic. Right? So you could see, you can go back into the history and see what were the topics that were the hottest, overall. And then look at their evolution, their quote-unquote hotness over the time. Now this has nothing to do with computer science. This is all about sociology of science. But we get to do it. So they could say, for example, that topic 37, 289, and 75 used to be pretty darn hot around 91 time frame, but then they sort of fell down in popularity. Instead, on the other hand, topic 2, 134, and 179 used to be very, somewhat lower in popularity, but they increased as time went. It's just a way of analyzing large amounts of data. Okay, so there was a question in the very beginning as to how can statistical models, which are just, you're talking about, each document is just a random, set of words, randomly chosen set of words. How can it lead you to do any useful kinds of analysis? Here is a kind of analysis, and to the extent that you find it useful, then you are. It doesn't tell you what did paper number 75 say. It doesn't tell you that. Okay, but it does tell you exactly what the topics are and what are the hot topics, what are the not so hot topics. And I believe, if I am not mistaken, if I go to Family Desktop and then look at Microsoft Academic Search, they also have this for computer science. Oh, come on. Oh. Yeah, you should not be asking Microsoft. Oh, not good. Maybe that when you choose as your search engine Google, Internet Explorer removes a certain few words and puts some other words and sends it. Anyway, here, computer science, right? So there should be, I think, in the keywords. So these are the top keywords. There is some place where I remember they were also talking about topics, which are basically distributions over keywords. The point is, this has become easy to do. The stuff that you're doing has become easy to do, so everybody does this. And that way you can actually say, well, these are the topics that seem to be hot versus cold in the current scenario. And if nothing else, they provide sort of a statistical validation to your own prejudices. Okay, so for example, you send a paper, your paper doesn't get in. Oh, it's important stuff, but somehow people don't seem to be thinking about this. And then you do this, and yeah, that's true. Actually, everybody is doing big data, and you are the only guy left out of big data, and that's why your paper is not. Okay, so what I'm going to do, I guess, in the next class is to go through the inference part, which basically would be using collapsed Gibbs sampling to compute PZ given W, and from there get those topics. Absolutely. Okay. Thanks.